Hi everyone, I'm going to be going over question 9.36 from the in-class bingo problems. This problem says a wheel is turning about an axis through its center with constant angular acceleration. Starting from rest at t equals 0, the wheel turns through 8.2 revolutions in 12 seconds. At t equals 12 seconds, the kinetic energy of the wheel is 36 joules. For an axis through its center, what is the moment of inertia of the wheel? So first of all, so I've already written down kind of what the problem gives us, and then our main objective, which is the moment of inertia. I guess the only thing isn't explicitly in the problem that I have written is that the initial angular velocity is 0 because it starts from rest. But first of all, let's convert this angular displacement into radians, since revolutions really aren't much use to us without converting. So we'll do that first just to get it out of the way. So we know that 8.2 revolutions, we know that 1 revolution is equal to 2 pi radians. Revolutions cancel, we end up with radians. So our angular displacement in radians is actually going to be 51.52 radians. Okay, so now that that's out of the way, I like to convert things first just because I know if I don't do it first, I'm going to accidentally plug it in thinking it has the right units and it's not going to work. But anyway, now we can kind of get into the problem itself. And the first thing we're going to want to do is we're going to want to find the final angular velocity. And so to do that, we can use one of our kinematic equations that says that the angular displacement is equal to the initial angular velocity times time plus 1/2 alpha t squared. And of course alpha is the angular acceleration, t is time. So the nice thing is that when we do this, this initial angular velocity is 0 since it's starting from rest. So we can just cancel all of that. That's just equal to 0. So to rewrite it a little cleaner is and I guess I didn't really do a good job explaining what we're doing here. We don't know the acceleration, and so in order to find the final angular velocity, we need to find the acceleration first. And so to do that, now we can just isolate, and we end up getting that the angular acceleration is equal to 2 theta over time squared. So now that we've done that, we can plug this into one of our other equations, which is that the final angular velocity is equal to the initial plus the acceleration times time. And what we can do now, since we've solved for the acceleration already, is we can plug this in there. So we can get final angular velocity equals the initial plus 2 theta over t squared times t. And so since we had found that, this is going to be really easy to work with. Because we know that the initial is just 0, so, and then we can cancel this t with this t down here, or the squared at least. And so once we clean that up a little bit, we get that the final angular velocity is equal to 2 times the displacement over the time. And so now we can plug that in, and we end up getting that that final angular velocity is equal to 2 times, and our displacement, since we already converted that to radians, we get 51.52 radians over time, which is 12 seconds. Plug that into the calculator. And we get about 8.58 radians per second. So I'm going to write that up here to keep it out of the way. Alright, so we're almost done now, because now what we can do is use one of our energy equations, which states that the kinetic energy, I'm going to switch, this marker's not doing the best, say that the kinetic energy is equal to 1/2 times the moment of inertia times the final angular velocity squared. And now what we can do is we can just solve for I. So we end up getting that I is equal to 2 times the kinetic energy over the final angular velocity squared. Now we just plug in the values. We have values for these, and so that goes to I is equal to 2 times K, which is 36 joules, over and that is 8.58 radians per second squared, and throw that in the calculator. We end up getting that the moment of inertia is equal to about 0.98 kilograms times meter squared. So that is question 36. So it's kind of a long one. We had to use a lot of equations, but hopefully you can see how we needed to find that final angular velocity. And we did that through finding the acceleration, and then we were able to plug in that final angular velocity into our energy equation to solve for the moment of inertia. So anyway, I hope you enjoyed watching, and I'll see you in the next video. Thanks.